speaker today is Sander from Museum.
I'm very, very happy to speak to such an esteemed audience, and in particular an audience which is so familiar with this material that I'm a bit scared, because I'm going to be picking some fights with people, basically with almost everyone, but more with some than with others. And I'm not exactly sure how big the fight is with people from a potential outcomes camp, because I don't know as much about that side from the causality world than I do from the Pearl camp. So everything's going to be starting from the Pearlian framework, because that's what I know best, and also because Pearl is, as far as I can tell, much more explicit about what his views are underlying where counterfactuals come from. So it's an easier target for me to attack because I understand what he's saying. What I'll be doing at a very high level is there are some issues or assumptions built in to the semantics of counterfactuals as Pearl defines them, which have been quite controversial for a while. In particular, Philip David has written this very influential paper in 2000 criticizing those assumptions and, very roughly put, thereby dismissing counterfactuals altogether, unless they can be reinterpreted as if they're actually interventional. Then it's fine, but the moment they're proper counterfactuals, then basically, because of all these very strong assumptions, which you just not have anything to do with them. And this is, a lot of commentaries were written amongst some of the people in this room provided lots of responses, trying to defend counterfactuals. But the debate is still ongoing. And just a few years ago, it took up again because there's a focus on how to think about harm in precision medicine. And Pearl suggests, well, this is a counterfactual notion. And there, Philip David saw an opportunity to once again express his skepticism regarding this notion. And therefore, it's not just a purely academic exercise. It has consequences for how you're going to think about policies in medical settings, what your views are on counterfactuals. The bigger background here is that originally I come from philosophy, and in philosophy there's lots of work on counterfactuals, and there has been for about 50 years or so. And although there are some connections to what's been going on there and what's happened in the causality world, they're not as strong as I would have expected. And so the strength of the assumptions that are built into the semantics of Pearl has not been recognized as such, I think, because in part there's not that much awareness of the broadness of the views on counterfactuals in the philosophy literature. That's background. I'm not going to get into that too much. I should also mention that this is in memory of Joe Halpern, who, as most of you are aware, I assume has passed away, sadly, just over a month ago. And he has been influential globally in terms of thinking about counterfactuals and causality, but also personally, I've learned a lot from him. And also in this paper, he's been influential in formulating my thoughts, although I'm sure he wouldn't agree with everything I'm going to say right now. And I'm going to focus on one paper that is currently under review, which is a bit more of a conceptual paper backing up what I'm saying in some other work, where I didn't dive into it that deeply, but just to show you that if you are really obsessed with what I've just said and you want to know more about it, these are all papers that you can have a look at, focusing on different aspects of it. In particular, the first paper is focusing on the logical aspect, relating it to the logic of counterfactuals. Here, I'm going to focus exclusively on the probabilities of counterfactuals. As I already mentioned, there's this very big debate that's been going on since 2000. And simply put, you could see it as Camp Pearl versus Camp David, but there's a lot more people involved in it, and potential outcomes are, I'd say, mostly associated with Pearl because potential outcomes are, they have counterfactuals built into them from the very get-go, so surely they will want to defend the meaningfulness of them. But as we'll see, perhaps there's some room for, in the middle, for potential outcomes people as well, because it's not that clear that these assumptions that Pearl makes are necessary requirements in the potential outcome framework. Now, to start, before we even start thinking about counterfactuals and causal models and what to think of them, first question to ask is, all these models are expressed with variables. I think it's absolutely crucial to focus on what are good variables. And in philosophy of science, this is a huge topic, right? What are meaningful variables? And that's where I'm going to start with. I'm going to say, let's take the cleanest case possible of what a scientific model should aspire to. Even perhaps in unrealistic, let's take that as our idealization. That's the best setup. Let's think about counterfactuals in that situation. and figure out how it works. And then afterwards, if you're saying, well, I don't have this ideal situation, fine, then you can start thinking about how you want to approximate what's being said there. But at least to understand what's going on, we should start out with the cleanest case of causal models that we have. And I would call those realistic and complete causal models. Realistic refers to the variables. They should refer to something real. And this is going to be the crucial element of the dispute with Pearl, because his semantics relies on response variables. And I'm going to push back against the very idea that these response variables are real, and therefore we should get rid of them. They should also be complete, by which I mean we should assume that the variables in the model are such that we've captured everything that is required to speak about counterfactuals, so that there's no room for skepticism in terms of perhaps there was some missing variable there, and that's doing a lot of the work, so we can't be sure what the semantics is. So that's why, per assumption, I'm going to assume this is a causal model for which that's not the case. We have all the relevant background variables, so the causal model is complete. This is going to relate to the notion of causal sufficiency, but it's going to be even stronger than that. I'll explain in a second. So formally, I'm going to put out all the definitions there, but you don't have to read them. It's just if in the Q&A somebody wants to really pinpoint what exactly do you mean there, I can refer back to them. But as such, you all understand broadly what these definitions are about. The signature is just telling you that we have variables which are split up into two sets, exogenous and endogenous. Right? The exogenous ones are the ones which we take for granted. They don't have any further causes. And the endogenous ones are the ones regarding whom we want to speak about causal relations. And they all have a particular set of values that they can take that comes with the variable. And we can also speak, of course, about of sets of variables or vector of variables and the domain over those sets of variables. Now, the realistic property, or the realism comes in simply by the informal condition. So I can't define formally what that means, but just informally, if you choose a variable in your model, make sure it represents a real property. There's something out there that it's measuring. With endogenous variables, it's taken for granted because these are usually called the observed variables. So, well, if you can observe it, it must be real, unless, of course, there's a mad demon there deceiving us, but taking that aside. Exogenous variables, there it's a bit fishier, whether those have to be, or whether those are always taken to be real or not. So I'm just from the get-go saying, also these exogenous variables, if you're putting them into your model, you should have some kind of sense as to what they're referring to, what kind of property. Doesn't mean you can observe them, but at least you should have a sense of what is it about the world that is determining the value of this variable. If you don't have such a story about a variable, it shouldn't be in your model. And I think this is broadly a kind of accepted criterion across science, right? That your variables in your model, if you're a realist, they should represent something. The other part that's crucial is that they're separable, by which I mean separate variables, the properties that they're referring to don't interact with each other. They're speaking about different parts of the world. And to make that concrete, it should be, in principle, so logically possible, if you have variable x and variable y, that any value of x and any value of y are compatible. Maybe empirically it's impossible. It could never happen due to laws of physics or whatever. But at least you should be able to imagine, oh, x takes on this value, y takes on this value. What does that mean? So there's no semantic, logical relations between these variables. And why is that important? Well, it's particularly important if you go with the Pearlian view where all endogenous variables are up for grabs for interventions. Right? Because if you say, look, I can intervene on all my endogenous variables at the same time to set into any combination of values, well, then your language is already making statements about any possible combination of values. So it has to refer to something sensible. I do realize that the assumption that you can intervene on all the endogenous variables is very strong. So perhaps people would not want to make that. But even if you don't make that assumption, I still think it's a very sensible principle of modeling that you should make sure distinct variables are not referring to the same thing in the world. And the same goes for both endogenous and exogenous variables. And there, the reason is because the exogenous variables are referring to what you might call a context, background conditions. And each context should be logically compatible with any setting of the endogenous variables. So also there, the properties should be separate. The completeness part, there shouldn't be any direct causes. Why is this stronger than causal sufficiency? Because causal sufficiency usually only refers to common causes. Right? So for the endogenous variables, if there's any common cause, it should be represented by an exogenous variable. Here I'm saying any cause. Even if it's only a cause of one endogenous variable, it should be in there. The reason being, if you want to have all the information that could be potentially relevant for determining values of counterfactuals, you want to make sure that all the causes are in there, so you can somehow separate off this model from everything else in the universe. Okay. The idea of an extension simply means we could have a causal model and we can extend it with further exogenous variables if we feel that we don't have enough of them yet, to make sure that if we have an incomplete realistic model, how could we add further variables to make it realistic? And of course, we're going to have a DAG, which represents the causal relations between these variables. That's all standard. And so taking these components together, I define a causal model as follows. And you don't need to read it. Essentially, it's a causal Bayesian network. Right? That's what Pearl calls it, and many people call it, but I'm taking that as the definition of a causal model. So this is the ground truth. Right? This is describing the complete description of our little part of the world that we're looking at. So we have a signature, a graph, and a probability distribution. And the DAG has to be such that all the exogenous variables, they're also in the DAG. Right? I'm not leaving them out. They're in the DAG, but they're root variables. And then I'm going to assume that it satisfies the Markov property. Not because I think you can always find a realistic model which satisfies it, but just because I don't know what the semantics would look like if you don't have that. So I'm currently working on trying to generalize it, but now, just for sake of starting somewhere, I'm assuming that we have a Markovian model, which simply means that the joint probability factorizes, as you're all aware. Yes?
I just wondered, do you want to take questions during the talk?
Clarificatory questions, of course.
I don't know if it's clarification, but in your previous slide, when you defined your extension, it seems that you only extend the exogenous variables. So why is that? Why can't we have more endogenous variables?
Well, we could, but it's not going to be required. The idea is that the exogenous variable is going to be having to do the work of if a model is not yet complete, you can always make it complete by adding exogenous variables. So you wouldn't need to add endogenous variables just to get to completeness. But of course, if you want, you could also start adding endogenous variables. It just won't be that relevant.
Okay, so formally, how do you distinguish exogenous and endogenous variables in this setup? In the signature, you just called them.
In the signature and in the graph, you could say the root variables, those are exogenous. That and also the language. The formal language will not allow interventions on the exogenous variables. So counterfactuals will always be relative to a particular setting of the exogenous variables. And you can think about what if the endogenous variables were different, but you're always holding fixed the exogenous variables. But as such, that's a choice, that a convention has been adopted. You don't need to make it. You could also think about counterfactuals where you change the exogenous variables. So we get this famous factorization, right? So each variable is dependent only on its parents. And the exogenous variables don't have any parents. That's why they're all independent. So this is just the Markov property spelled out in terms of the distribution. And we can define the intervened distribution in a standard way. Namely, we take this factorization. If you're intervening on a bunch of variables, you're just going to drop the factor relating to those variables. And the joint distribution that's left, that's what you're now working with. And of course, you only allow solutions such that the complete solution satisfies the intervened values. So this is still Pearlian, except that I'm starting with the probabilistic level as the fundamental level. So what distinguishes this is that Pearl says, sure, we like to work with these causal Bayesian networks. They're very useful abstractions. But at the end of the day, there exists a ground truth which is even more refined. Namely, there's a ground truth which is deterministic. And deterministic means that all these probabilities here, except for these, all these probabilities should be 1 or 0. And if we don't have that yet in a model that let's say we've been working with a model, we don't have that, well, then we just need to extend. We need to add more exogenous variables. There's variables we must be missing such that we can find a complete model such that it all becomes deterministic. And he's quite explicit that in his book, he adopts the Laplacian quasi-deterministic conception of causality, as he calls it. And so what we then get is a structural causal model, which is exactly the same thing as we just had, except that all the probabilities that are not on the exogenous variables, they're all going to be 1 or 0. And so we can write that as if we have equations, right? That equations are simply extremal probabilities, so that for each endogenous variable, we have an equation telling us what its value is going to be in terms of its parents. So this is simply the deterministic version of a causal model, but Pearl assumes that we always have a way of extending the model such that we arrive at this. And this is an extremely strong assumption that has been criticized, rightly so, by Philip David, but it's a foundation of his semantics for counterfactuals. Also, Pearl is very makes very similar comments regarding the completeness is already there because of the fact that we have determinism, so there can't be any missing parents because you know what the value is going to be, so there's no information left to miss. The realism regarding the exogenous variables, he makes comments at times where he seems to support realism. Right? So here's a quote in which he says, in short, U summarizes all the factors which determine, in the classical physical sense, the outcome of the study. PU summarizes our ignorance. And so these are going to be missing details like the physiology, previous history of each person, mental and spiritual attitude. So all real properties that we might simply not know a lot about, these are going to be captured in the exogenous variables. And so if we have an SEM, we can define a counterfactual as follows. This is an unusual version of it, but that's because I want to have the probabilistic representation in there to compare it later with what I'm doing. But I can just explain it in words. We start with a basic counterfactual. That means, given that we have a specification of all the values of the variables, so including the endogenous and the exogenous, right? So this is the actual world, you can call it. What if we now think about the probability of the endogenous variables if it were the case that some variables x were set to x? Right, so we start with an actual world where all these things are true. Now we're imagining what would the probability distribution be if, in fact, x were set to x. And of course, it's really counterfactual if x is conflicting with v, although it's not strictly required. And how does Pearl define that? Well, we already know how to think about interventions. So we just apply the intervention, that's it. And the reason this works is because we have an SEM. So U does all the work. Once you give me the U's, I can plug them into the equations. And by the way, I've assumed acyclicity here, right? Once I plug U into the equations, I get a unique solution. So the probabilities don't have to do any work anymore if I condition on U. And so the intervention and the counterfactual stipulation, they both amount to the same thing. You just get rid of the equations for x, you replace them with constant equations, and that's it, and you just solve. So I've written it here as a probability just for generality, but you don't need probabilities. Concretely, how it works is you remove the equations for x and replace them with constants to solve it for the setting, and then you see whether or not the particular value of the v's that you're looking at is equal to that solution or not. And so you get 1 or 0 as a probability. Okay. If it is the case that we have an SEM and it's all fine, it's all realistic, I accept this. This is a very sensible story about counterfactuals. But what if we don't? What if we have a complete and realistic causal model which is not an SEM? Now Pearl will say, that's impossible. If it's complete, that means you've added all the variables that are relevant. But you can always find enough variables such that it will become deterministic. And so he doesn't consider that case. And I think that's extremely restrictive, right? Because I don't think we should assume such kind of determinism, and many others have thought similarly. And I'm going to give you an example such that even if you don't want to make any assumptions about the most fundamental scientific laws like quantum mechanics and all that, even if you say, look, fundamentally the world might be deterministic, then still there should be room for non-determinism because it's all about the variables. So I'm going to show you a simple example for an SEM, and I'm going to make one assumption, namely that these variables are fundamental, by which I mean there does not exist a realistic, more fine-grained representation of the properties that are being referred to than the ones given by these variables. Now, I'm making that assumption purely to avoid a logical loophole that someone could use to push back against this example. So if someone believes that it's really impossible ever to give a fundamental description, okay, fair enough, but that seems a very strange position. So I'm just making that assumption here. Assume we have an SEM where we have the most fine-grained representation of the relevant properties. And so we have some exogenous variables captured by U, right? So it's bold, so it should be a set, so there's multiple. And we have one endogenous variable v. We have one equation. Assume also positive distributions for both of those, so all the values can occur with probability more than 0. And also that there's at least 3 values for y. So certainly that doesn't sound like too crazy of a model to consider, right? Okay, now I'm just going to construct a new variable, z, which is binary, and which corresponds to the property whether or not the exogenous variables are one particular context. So u prime is just one valuation of the context, and it corresponds to z being 1. So if z is 0, all you have is the disjunction of all the other possible states of u. Now, I want to have realistic complete models. Well, u was realistic, so z is realistic, right? It's just coarse grading information that is realistic. U and y were separable, so also z and y are separable. So if I now change the signature to the one where I replace u with z, it's still a realistic signature. It's quite easy to show that this is not going to be an SEM, because the probabilities are not going to be just 0 and 1, right? If you condition on z equals 0, you don't know exactly what value of u that's going to correspond to, so that's going to give you a probability which is not 0 or 1 for some value of y at least. Now, the crucial point here is that there does not exist a realistic and causally complete extension of this model such that it is an SEM. And the rough idea, so I have the proof on the next slide, but I'm not going to walk you through it. The rough idea is simply that to extend it, you need to have an additional variable, w, to somehow make up for the fact that if you know that z equals 0, you don't know enough. So you'll have multiple values of w to compensate for that. But then if you consider z equals 1 in combination with this variable w and all the possible values for w, well, z equals 1 corresponds to one value of the u. We have now multiple values of w, and these are separate variables. But we assume that w is the most fundamental description of reality. So we get a contradiction. Like we have now multiple values which all correspond to one value of u, and the values of u were supposed to be the most fundamental. So somehow, just by coarsening a variable, we are forced to accept that there exists an even more fundamental level of description, because otherwise the math doesn't work. Right? Essentially, that's the idea. That's why the idea of assuming fundamentality I don't think is that fundamental. It's just to avoid the loophole of just somehow someone being able to say, what if there's even a more fine-grained description than u was? Okay. And this is an example with just one outcome variable, but you can take a very, very simple instantiation of that, such that now you have 2 outcome variables to show that the Markov condition does not hold, and also there's no way of extending it in a realistic way such that the Markov condition holds. Now this is crucial because there's been a lot of debate about whether the Markov condition universally holds. In other words, is there always a set of variables you can find such that if you have a model which currently doesn't satisfy the Markov condition, can you add them to get the Markov condition? And certainly in the graphical framework, it is assumed that that is the case. They defended very strongly against criticism by both Philip David, but also Nancy Cartwright, dating back to the 90s. And the example, by the way, to give you a sense of it, if you may be familiar with this historical example by Wesley Salmon, think of a pool. In this case, snooker would be more appropriate. Imagine you have a snooker table. You have 2 balls which are laying right next to each other in the middle of the table. And there's a white ball which is going directly at it. And we're considering whether or not the white ball hits the 2 red balls or not. And since they're lying in a symmetric triangle relative to the pockets, essentially if it hits it and the one goes in, then the other one goes in as well. So if you describe this situation just with the binary variable, does the cue ball hit or not hit, then even though these are different outcomes, once you condition on their sole parent, namely being hit, they become dependent, right? Because knowing that the right ball went into the pocket gives you information about, oh, well, probably the left ball went into the pocket as well, because they were lying at the same angle. And this is an example given, and Cartwright gives many more. Most of them involve quantum mechanics. I don't want to get into that. I focus on purely deterministic situations, meaning fundamentally there's this deterministic description. The variables we've chosen are not at that level. And Hausman and Woodward and also Spertes and CMU people, they push back against this. And the standard response is, well, you shouldn't have picked such silly variables. Why did you pick that binary variable? If you were to have a variable which gives you the exact momentum of the cue ball hitting it, then all of a sudden we would have the Markov condition. It's like, sure, fine, but how, first of all, why should I be forced to restrict my attention to such variables? That would be such a limiting way of doing science. In fact, all of the social sciences are out of the window. Most natural language statements would be out of the window because they all contain variables which are not at that level. And should we abandon speaking about causation in those fields? Secondly, how do I know that I've specified my variables such that they are at that level? How can I find out? So instead of just saying there must exist some variables, okay, give me criteria such that I can find out whether or not those are the right variables. And such criteria in general, I'm not sure if we can come up with them. Certainly they haven't been proposed. So the moral of the story here is that even if you assume there's some deterministic description of the world, in many situations we will have variables such that not only is a situation described relative to those variables non-deterministic, we cannot extend the model keeping those variables in it such that it becomes deterministic, violating what Pearl believes is the way of getting down to SEMs. Now, this might give you, there might be a natural suggestion here, certainly for anyone who's worked on abstractions, which I have spent a lot of time on. You might say, wait a minute, in the example you gave, we couldn't have determinism at the high level, and therefore we couldn't use the SEM semantics there for but at the low level we did have an SEM. So couldn't we somehow try to think about counterfactuals in the high level by reducing it to the low level? In fact, that's what Pearl would do. That's his example is one instantiation of that, right? We had our graphical model with just probabilities, and the idea is, well, this is just an abstraction of a model with more variables, and in that one we can actually think about counterfactuals, and I'll show in a second how that works. Now, the tricky part here is that causal abstractions, as I've defined them and as many others have worked on, are still sitting in the camp where both of the causal models are SEMs. Both the low level and the high level are SEMs. That is not the situation we were facing. We were facing a situation where the high level was not an SEM. So we need to generalize then causal abstractions. And there's several problems with that. Some are problems in terms of why should we, others are more technical. So let me first focus on why should we. What if there is no such low-level SEM? In the example I gave, I assumed there was, but should we always assume that that's the case? Again, this brings back the assumption of universal determinism. And as Cartwright puts it, this assumption of universal determinism in causality, it's either a piece of metaphysics that should not be allowed to affect their scientific method, or an insufficiently warranted generalization from certain kinds of physics and engineering models. So if you simply look at all of the scientific models that scientists are working with, many of them will not be deterministic and will also not be of the kind where they somehow believe that eventually a deterministic representation will be given. Right? In some areas, there is a goal of trying to somehow fill in the gaps, but that's certainly not the case in all the sciences, especially as you go higher up. And even in biology, there's lots of talk of stochastic processes. So the solution I just proposed of going down to the low level might not be an option, first of all. Secondly, the high-level ambiguity or indeterminacy could very well be a feature, not a bug. So most of the concepts that we have in the social sciences and natural language, it's not that we didn't decide to make them more, it's not that we don't know yet what the relation is between those high-level concepts and more fundamental physical concepts. It's that we don't want such a relation because we want the ambiguity of these concepts to exist. It's something we cherish. There's lots of concepts. These are just a random list of concepts which I think can play perfectly fine causal roles. And in fact, in everyday language, we use counterfactuals involving such notions all the time, right? Acting like an idiot. You can have that as a variable and say, look, why was a student expelled from class? Because he acted like an idiot. Counterfactual, if you hadn't acted like an idiot, he wouldn't have been expelled. It's a perfectly meaningful statement. Yet there's no way of saying what are the physical conditions that uniquely determine for once and for all what it means to act like an idiot. And why would you want such a story anyway? Also, even if in some cases there could be such a story to be told, often we don't care because scientific models, after all, are idealizations. And often we don't care about the fact that they're somehow realized in a particular way. So we would like to work with these idealizations directly. That's why I say abstract the abstraction. The fact that there might be more fundamental description, we want to somehow abstract away from that and just take this higher level representation as the thing that exists. And one example, which is quite prominent, is computer programs, which includes, of course, all of AI. If you describe these, you can describe them in many levels of abstraction, but at the end of the day, they're implemented on deterministic machines. Right? All stochasticity is due to pseudo-random number generators. So we could try to look at exactly how it's being implemented, look at the physics, and figure out a deterministic representation of any computer program. That would be absurd, right? And almost never happens. Like most of the studies of properties of computer programs take some probabilistic properties of these programs as just primitive. That's what I certainly argue for in the case of LLMs. When we're thinking about counterfactuals in LLMs, that's what one of the papers I mentioned focuses on, that LLMs, if they're acting with a high temperature, meaning that they don't always get the same answer, all we have is a distribution, and we should take that distribution as if it is truly random, regardless of the fact that we're implementing it on a particular CPU, which has a particular way of choosing the seed. That shouldn't be relevant. Okay, lastly, even if you set aside all these issues, technically it's not that easy to work out this proposal of somehow generalizing abstractions. One thing it already requires, and this is just one out of many things you have to do, is give a semantics for disjunctive interventions. Because what you're going to have is at the high level, one value is going to correspond to a disjunction of values at the low level. So intervening at the high level will mean a disjunctive intervention at the low level. Figuring out what that means, Pearl has tried it, and he gives some suggestions, but he said, look, all these suggestions are kind of ad hoc. It's very hard to come up with a principled way of doing so. And ironically here in this context, he says, caution need be exercised when metaphysical extensions are taken literally without careful guidance of decision-making considerations. Now in this case, he seems very skeptical of making, basically reifying metaphysical extensions, but in other situations, he's not so careful, and that's what brings me to how he would handle the problem of counterfactuals in models that are not deterministic. So let me quickly go through this, because this is all, I'm assuming, common knowledge for you. What he does is we can represent a probabilistic model as an SEM by using response variables. So we can think of a canonical frame where we simply add additional exogenous variables which capture all the work that is being done by the probabilities, such that essentially what you need is a function that maps from all the existing parents to the child, and this function itself is going to be now the value of a variable. In this way, you can mathematically represent all the possible outcomes for any probabilistic process, and you can then pull out the probability and put it on this response variable. Right? That's what happens in trying to identify the bounds of counterfactuals. This is the method used. And all these SEMs have exactly the same structure. The only difference between them is what is going to be the distribution over these response variables. There's, of course, going to be a constraint. You need to have it such that the marginal distributions should fit the ones that we already know are the case, right? That's the constraint you have. Other than that, there's many possible ways of filling it in, and that is why we have partial identifiability only, unless you make very strong assumptions instead of point identification. Right? Very simple example. If you just have binary variables x and y, you have probabilities which are not extreme, and you have now you can, if they're binary, the response function will have 4 values because there's 4 functions from one binary variable to another. And you now need to give me a probability for each of these functions being realized. Once I know which function it is, I can identify the counterfactuals. But there's many ways of filling in those probabilities such that you would arrive at the same marginal probabilities. So that's why you could even get, in many cases, uninformative bounds where it could be 0 or 1. But the main idea here is the counterfactuals in our causal model that was probabilistic, they reduce to counterfactuals in the deterministic model. So the entire semantics is resting on that reduction. Now, what are these response variables? Are they artificial or real? As I previously already cited Pearl, there he seemed to be on board with the realism of exogenous variables. It was referring to properties of a person. But this statement is quite revealing. because here it says the value of a response variable may stand either for the identity of a unit, example, person's name, which is nothing else but a way of representing a data point, right? That's it. It doesn't reflect any real property in the world other than, oh, I'm referring to this person instead of that person. Or more functionally, a set of unit-specific characteristics. Now, those are real properties, right? Things about this person, the real properties. But so the fact that he's jumbling these two together, to me, points to the fact that he's not sufficiently aware of how crucial it is that we can have different interpretations of these response variables. And now coming back to Philip David, so he also argues for realism, and he says, therefore, we shouldn't go with we shouldn't go with the artificial interpretation, but the realistic interpretation, similar to Cartwright. So I'm just giving you these quotes just to show you that I'm not making this up as like an idiosyncratic preference. The realistic interpretation of response variables requires such Laplacian determinism that is out of favor as a general scientific or philosophical principle. And more importantly, even if you believe it somehow is true, it seems very odd to make it the cornerstone of a general theory of causality. Good. So now that we have the problem set out and we have Pearl solution that we kind of, at least I have dismissed and disagree with, what is the positive story here? Because I don't have that much time left, but I can give you the essence of it. And potential outcomes comes in as follows. Response variables, to me, are very dodgy because they're entirely somehow artificial. I think potential outcome variables are somewhere in the middle. So in the other paper I mentioned, I give an alternative semantics, and I'll come back to that in a second, which don't at all add any further variables. They just keep the probabilities as is. What I'm doing in this paper as an exercise, because it starts with the Pearlian framework and then just starts to remove the parts that are artificial, I'm using this semantics as an exercise to say, how does this relate to Pearl semantics? What exactly did we change? But as it turns out, the semantics that I arrive with here is equivalent to the one I proposed earlier. That's one of the results of the paper. So what happens? We can have this canonical representation of any causal model with response variables equivalently expressed with potential outcome variables. Now, crucially here, potential outcome variable are taken to be such that we include all the parents, right? So it's not just that we're indexing it with one treatment variable. The idea here is all the parents are relevant. So including the exogenous variables, whatever, because we're dealing with a complete causal model, right? So the subscript PAX here means we've got included all of them. And so for each possible value of the parents, there's going to be one potential outcome variable. And then you can translate between this response variable formulation and the potential outcomes one, because the response variable is simply a list, you could say, of all the values for each response variable, for each potential outcome variable, right? It just tells, it's a function. So for each possible value of the arguments, there's one outcome. So you can separate that response variable, split it up into a set of variables, and these are the potential outcome variables. So we had our previous representation where Fy was this response variable, and we can express that equivalently with just saying, look, if these are the particular parents, you should look at that particular potential outcome variable. And then we can represent all of this as an SEM with just having these potential outcome variables, and also make sure that the constraints are met that we already know. So the distribution for each potential outcome variable should be such that it respects the distribution of any variable upon its parents. Now, what we had with the canonical SEM previously was there were lots of choices. Here, choices disappear. Why? Because we've now already established that this should be the marginal probability for each potential outcome variable, but we're working with an SEM. SEMs have independent exogenous variables because of the Markov condition. If they were dependent, there should be an additional variable there that we missed, so they're independent. So that means a joint distribution has been specified now as well. So there's only one distribution. So we have unique identifiability. And just to give you, again, the same example, to see what it looks like in practice, binary variables, we're going to have two potential outcome variables, namely for each possible value of the parent. And then the equation is simply that the value of y is going to be the corresponding potential outcome for the parent value that's realized. And we have our probabilities here The same story as with Perl, counterfactuals in our probabilistic model reduce to counterfactuals in our SEM, except that things look much cleaner because we have point identifiability. So this is the probability of, just the observational probability of y1 given x0. If we now ask the following counterfactual question, given that we observed x equals 1 and y equals 1, and we're now reasoning about what if x would have been 0, what is the probability of y being 0? It's just going to be 1 minus q. In other words, it's just going to be the probability of y being 0 given that x was 0, the observational probability. Now that's true, of course, for this very simplistic example, but in general, it will be the case that these probabilities are going to be much closely related to the observational one. And a very similar derivation, by the way, is found in a paper by Philip David with Monica Musio, where they also consider, what if we want to give stochastic counterfactuals a chance? They give a derivation of a similar kind.
Yes.
Sorry, why don't you get partial identification here? What's
the magic trick? The magic trick is the independence of exogenous variables. So we have now no longer one response variable. We have multiple exogenous variables which representing all the potential outcomes, right? So in other words, each potential, and so we have to set their marginal probabilities to the observed ones, just for consistency with the probabilistic model. But that means everything's been determined because we have the marginal probabilities. They're exogenous variables, therefore they're independent. So it's yes. So this is, of course, the point where you're going to say, wait a minute, that's a very strong assumption. And I have 2 minutes to convince you of that. Now, here's one story. First of all, in the other paper, I don't use the potential outcome variables, and yet it ends up in the same semantics. So one very brief summary of an argument there is, look over there, I get the same semantics without talking about potential outcomes at all. But to give you at least some motivation in terms of the framework I've just given, the focus was on realistic variables. Now, these potential outcome variables, they're still unrealistic to me because they were speaking about other worlds that were not realized. But yet, we can always choose, there's always going to be one potential outcome variable that is going to be realistic because there's one world. So there's going to be one thing that actually happened. So at least we can refer to, in this world, these things happened. And the potential outcome that corresponds to the actual values of the parents, that's going to be just a proxy for what actually happened in this world. So in other words, if you think about the process of what's happening, first, the parents of X are being realized, so they get a particular value. Okay, at that point, the probability for that potential outcome is simply nothing but a representation of the prior distribution of X given those parent values. It's just representing a prior distribution, right? We don't know yet what X is going to be. It's a stochastic process. Then at some point, X takes on a value. And this is represented by the fact that the potential outcome has now taken on a value as well. This is nothing but a representation of the posterior distribution that we now know what the value is of X. So these are real in the sense that they're just representing probabilistic properties that have been actualized in the world. Whereas all the counterfactual outcome variables, so the naming, by the way, so the potential outcome corresponding to what actually happened, let's call that the actual outcome variable. The potential outcomes which correspond to everything that did not happen, those are properly counterfactual outcome variables. They're just artificial mathematical constructs that we use to get our semantics to work because we want to be able to speak about the same probabilities occurring in these other worlds. And we found those tools useful, but they're not in any way real. The values that they take on, it's not as if we don't know what their values are. Their values don't represent a real property. So it's not as if we are epistemically are limited. It's that it wouldn't be sensible to give them values, and that is translated into the mathematical property of independence. Now that I also had a different story to tell you, which I was going to. I'll keep that for the Q&A because I'm sure I'll get some pushback on this. So I'll now move just on to some of the results. I gave two formulations in terms of FCM, the Pearlian one and the potential outcome one. You can prove quite easily that there always exists one Pearlian SCM which is going to correspond to the potential outcome one. Okay, so that's just one result. So in other words, it's a refinement, you could say, of the Pearlian semantics. I also gave a semantics without any additional variables in previous work. And again, the semantics agrees. So this is the semantics I gave previously. This is the one using these potential outcome variables. they agree. And that's for the basic counterfactuals, but also for these kind of simple counterfactuals, as well as the probabilities of necessity, sufficiency, and causation. What is the other one? Necessity and sufficiency. And then lastly, there's also work by Galhotra and Halpern recently, where they also said, what if we just have causal Bayesian networks? Can we speak with counterfactuals directly? And actually, I proved that their semantics is also equivalent to the one I just proposed. Lastly, some people have talked about stochastic counterfactuals, in particular, Philip David himself. And what he says there is very congenial to everything I've said. It's just that for him, it's more like a reflection on a possibility, and it's not a fully worked out story. So I've worked it out, but it's still very much consistent with everything he said. So in his original paper, he imagines, well, what if we somehow assume that we do know all the complete variables, sufficient concomitants? And what if we assume that they're genuine and true, so they're realistic? Well, then, he basically says they should all be conditionally independent across complementary universe, so different worlds, if we know all the concomitants. And that translates exactly to the assumption I made, namely, once you know all the parents, these potential outcome variables are going to be independent. Similar comments occur in these papers, the details of which I was too scared to put on here because of the risk of making a mistake. And again, these occur in this work as considerations, not as fully blown endorsements of the semantics, but at least there are very much observations going in the exact same direction. Most recently, a paper involving Russian roulettes, where the exact same properties of potential outcomes are discussed. I will keep it at that because time is running short, but I'm sure I'm hoping there's going to be some critical questions from your side. So thank you for your attention.